Okay, so welcome everybody to the first seminar of this 2021. It is a great pleasure to me to introduce Carolyn Gordon. So she's from Dartmouth College, and today she's speaking about infinitesimal maximal symmetry of Richie Solitons on solvable Lie groups. Thank you so much, Carolyn, for accepting this invitation.
Well, thank you for the invitation. Córdoba, well, Falmouth is one of my favorite places anywhere, so it's just really wonderful to be here, even if I'm not there in person. This is joint work with Mike Jablonski, and please just interrupt anytime with questions. What I want to talk about is sort of the following general question. Given a Lie group, is there kind of a nicest Riemannian metric, left invariant metric on that Lie group? And there's lots of ways you could ask about nice. One way is to have the most symmetry of any metric. Other ways, of course, are to have nice curvature properties, have nice properties under a flow of some sort. And so what I want to look at is a notion of maximal symmetry and how it relates to other nice properties. So the outline, I'll introduce maximally symmetric left invariant Riemannian metrics on Lie groups, talk a little bit about existence, mention this part is kind of history, the maximal symmetry of Einstein metrics on solvable Lie groups. And then we'll talk about positive and negative results concerning maximal symmetry for Richie Solitons. And then because of the negative results, we'll introduce a weaker notion of maximal symmetry and show that expanding Richie Solitons are infinitesimally maximally symmetric. So, of course, all these things will be defined. So what do we mean by maximally symmetric? So we'll say a left invariant Riemannian metric on a Lie group G is maximally symmetric if for any other left invariant metric on the same group, the isometry group of H is contained in, I want to say it's contained in the isometry group of G. Of course, if you change G by an automorphism, you get something isometric, and the isometry group changes by isomorphism. So we can just say the isometry group of H is contained in that of G up to pullback by automorphisms. So that's kind of the strongest form of maximal symmetry one can have. Example is if you have a simple compact connected Lie group, then the bi-invariant metrics are precisely the maximally symmetric ones. Although if you take a compact semi-simple that's not simple, you might actually no longer have this result in general. So again, questions, which Lie groups a bit maximally symmetric, left invariant metrics, and are geometrically distinguished left invariant metrics maximally symmetric. Just a brief reminder, if you have a Lie group, we'll always denote by the corresponding Fraktur letter, the Lie algebra. Left invariant metrics on the Lie group just correspond to inner products on the Lie algebra. And of course, we have an inclusion of the Lie group in the isometry group of the metric, since G is acting isometrically on itself by left translations. And the normalizer of G in the isometry group just consists of G together with those automorphisms that preserve the metric. I'll call that OT sub orth for orthogonal. Or in other words, their action on the Lie algebra preserves the inner product. So here's a sort of simple existence result. For some Lie groups, we have the property that for every left invariant metric whatsoever, the isometry, that G is normal in the isometry group. And so the isometry group is contained in G together with the automorphism group. And a second, less important condition is that the automorphism group have only finitely many components. This will always be true if the group is simply connected. I'm including the second condition because that guarantees that Maxwell compact subgroups of the automorphism group are all conjugate in the automorphism group. And in such a situation, G will always emit a maximally symmetric left invariant metric. And the proof is just up to conjugacy in the automorphism group, there's a unique Maxwell compact subgroup of OT G. And so just take any metric that's invariant under such a Maxwell compact subgroup, and then up to automorphism, its isometry group will contain that of all others because of the first property. Now, there's a number of types of Lie groups that do satisfy this the hypotheses. All compact simple Lie groups do. All semi-simple Lie groups of non-compact type. All simply connected nilpotent Lie groups. All completely solvable. I'll define that later. Simply connected unimodular Lie groups. So in all these cases, any Lie group of any of these types will emit at least one, well, generally more than one, maximally symmetric left invariant Riemannian metric. So it is reasonable to look for such metrics. For other types of Lie groups, they may or may not. We'll see some examples of ones that don't a little bit later. Okay, so now I want to turn to the question of whether our favorite metrics, or some people's favorite metrics, are maximally symmetric. So let's first look at left invariant Einstein metrics on Lie groups. I want to say here, this first half of the talk, I think some of you may have heard before. The first half is kind of historical. The second half will be newer results. So suppose G is Einstein. So the Ricci curvature G is a constant times the metric. Well, the possibilities, positive Ricci curvature. In this case, G is compact and semi-simple. And in this case, there could be many Einstein metrics on G with very different behavior. And even the bi-invariant metric, which is Einstein, on a compact semi-simple Lie group need not be maximally symmetric. And so we're not going to look at this case. If Ricci equals 0, the metric is, in the homogeneous case, it's just flat, so that's not very interesting. And so we're going to look at negative Ricci curvature. And for homogeneous manifolds of negative Ricci curvature, the Alexievsky conjecture says that every connected homogeneous Einstein manifold of negative Ricci curvature is diffeomorphic to Rn. Now, this is still open. A lot of work has been done on this here quote, in Córdoba. A wonderful recent result of Christoph Bohm and Ramiro Lafuente is that if the Alexievsky conjecture is true, then every homogeneous Einstein manifold of negative Ricci curvature is actually a simply connected Riemannian solved manifold. Let me define solved manifold. So a Riemannian solved manifold is just a Riemannian manifold that emits a simply transitive solvable group of isometries. Anytime you have a simply transitive group of isometries, it will inherit a metric from M. And so M will be isomorphic to S with a left invariant metric. And so the Alexievsky conjecture now says that the only homogeneous Einstein manifolds of negative Ricci curvature are solvable Lie groups with left invariant metrics up to isometry. So that's what we'll be looking at. Mike Jablonski and I proved earlier that left invariant Einstein metrics of negative Ricci curvature on simply connected solvable Lie groups are maximally symmetric. So any other Riemannian metric will have an isometry group contained in that of the Einstein metric of tautomorphism. We gave a very kind of a complicated proof of this result. The proof we would have liked to give would be to use the fact that Einstein metrics are stable under or fixed points of the Ricci flow, but you need stability to get a proof. So we did things the hard way. Well, we got at this result in a rather complicated way. Now there's a much more beautiful proof by Bowman and Fuente using the Ricci flow, because they proved a stability result for the Ricci flow. So let me say a little bit about the Ricci flow. Are there any questions, by the way? Okay, so suppose you have a C infinity manifold, then recall the Ricci flow as a flow in the space of metrics. You flow by evolving the metric in the direction of the Ricci curvature. And the key point is that isometries are never lost during the Ricci flow. And so, I'm sorry that I have this containment going the wrong direction. What it should be saying is that the isometry group of the metric at any time will always contain the isometry group of the initial metric. It will never get lost. And Einstein metrics are fixed points of a normalized Ricci flow. So recently, Bowman and Fuente proved that if you have an Einstein solved manifold of negative Ricci curvature, then if you start with any left invariant Riemannian metric on the solved manifold, on the solvable Lie group, it will flow under the Ricci flow. It will converge smoothly to the Einstein metric up to pullback. And so therefore, because isometries are not lost during the flow, that says that the isometry group of any metric is contained in that of the Einstein metric. So that gives the right proof, I should say, of the Maxwell symmetry of Einstein metrics of negative Ricci curvature. Okay, so let's now move to Richie Solitons. So a reminder of the definition. So given a C infinity manifold, a Riemannian metric is a Richie Soliton if it evolves only by diffeomorphisms and homotheties, rescalings, under the Ricci flow. In other words, the solution to the Ricci flow, starting from with the metric G at time 0, is G of t is a constant depending on t, times the pullback of G by a diffeomorphism. So C here is a constant. Or equivalently, the Ricci curvature is multiple of the metric plus a Lie derivative of the metric, where X is the vector field generating the diffeomorphisms. Of course, if we don't have the second term, then we have an Einstein metric. So again, there's three types: C positive, the shrinking, C equals 0, steady, and C less than 0, expanding. The C equals 0 in the homogeneous case are still flat. Since we couldn't really deal with Maxwell symmetry for Einstein, we certainly, the positive C case, we can't deal with it in the more general soliton case. So we'll be looking at C less than 0. It's called expanding Richie Solitons. So first, a reason for looking at solvable Lie groups again. So combining work of Jorge Lorette and Ramiro Lafuente with work of Mike Jablonski, and then the recent work of Bowman Lafuente. So the final group, Bowman Lafuente, concluded that if the Alksievsky conjecture holds, then every homogeneous expanding Richie soliton is isometric to a simply connected solved manifold. So solvable Lie group with a left invariant soliton metric. So that's what we'll be looking at. So our standing assumptions throughout the rest of the talk is that all solvable Lie groups will be simply connected. All Riemannian metrics we talk about are left invariant, and all Ricci solitons will be expanding. So I may or may not actually mention that in the various statements. Now, within the class of all Ricci soliton solved manifolds, there's sort of a special subclass called the solved solitons. So let S be a solvable Lie group. Then remember, for Ricci soliton, it just needs to evolve by diffeomorphisms and homotheties. For a solved soliton on a solvable Lie group, we have the stronger condition that evolves by automorphisms and homotheties. So the diffeomorphisms actually are automorphisms to preserve the group structure. Not every left invariant Ricci soliton on a solvable Lie group is a solved soliton. There's some uniqueness results for solved solitons. So suppose a solvable Lie group emits a solved soliton, G, so the more restricted class. Then Jorge showed that G is a unique solved soliton on S, up to scaling and automorphism. Bowman and Lafuente, using their Ricci flow results, show that it's actually unique not only among solved solitons on S, but also among all Ricci solitons on S. And we'll see, I don't think this was known before, although it's kind of an fairly immediate consequence of things we'll see, that in fact, leaving the class of solved solitons and looking at all solitons, a solvable Lie group can admit at most one left invariant Ricci soliton up to scaling and isometry. I'm curious if that, because I know I'm talking to a number of experts here, is that known? Is anyone familiar with that? Okay. Okay, so I want to look at a result of Jablonski. I first need a definition. Recall Lie algebra is said to be completely solvable if every element of AD S has only real eigenvalues. So in general, the element of AD, well, it can have any type of eigenvalue. And so Mike Jablonski proved that if you have any solvable Lie group with a Ricci soliton, then even though that Ricci soliton might not be the stronger notion of solved soliton, there will exist a unique, completely solvable Lie group S and a solved soliton metric on S that's isometric to the original solvable Lie group with its left invariant metric. And that's going to play an important role in what we look at shortly. So a question, the main question I want to ask are left invariant Ricci solitons on simply connected solvable Lie groups maximally symmetric? Some positive results. Mike Jablonski proved that if you look at completely solvable unimodular Lie groups, and unimodular is key here, then solved soliton metrics on such Lie groups will be maximally symmetric. Now, completely solvable unimodular is one of the settings we talked about at the beginning, where the isometry group, where the group G of left translations, or S in this case, always sits inside the full isometry group as a normal subgroup. So the isometry group is just the group together with automorphisms. And that comes in heavily here in the proof. The recent work of Baum-Lafuente involving Ricci flow enables them to conclude again for solved solitons that the dimension of the isometry group of the solved soliton is at least as big as the dimension of the isometry group of any other left invariant metric. But it doesn't say anything about containment of the isometry groups, just the dimension. And this is for solved solitons specifically. Okay, I want to give a counterexample showing that left invariant Richie solitons are not always maximally symmetric. I need a little preparation first. So let H be a connected Lie group and let G be a left invariant metric on H. Then as we've seen, the semi-direct product of H with the orthogonal automorphisms acts by isometries. Now, among those orthogonal automorphisms, there may be some inner automorphisms. So let's let K be the set of elements in the group for which the inner automorphism preserves the metric. Now, observe that for A and K, since the inner automorphism is an isometry and all left translations are isometries, the right translations are isometries. And so the metric is left invariant under H and right invariant under the subgroup K. So we have an action of H cross K on H. So H cross K sits inside, well, I'm sorry, we have a mapping from H cross K into the isometry group, sending an element H of H and A and K to left translation by H. And to make this an action, we put an inverse right translation by A inverse. Now, this has a kernel coming from the center of H intersect K. So let D be K intersect the center of H. Then the kernel row is the diagonally embedded subgroup of the diagonally embedded subgroup of H cross K, consisting of, A, comma A, where A is in, again, K intersect the center, which is D. So you're just left translating by A and right translating by A inverse, and A is central. And so if you look at the Lie group H cross K, mod this diagonally embedded subgroup, then that sits inside the isometry group. The isotropy subgroup is the diagonally embedded subgroup K. Notice that K sitting in here diagonally is just acting by the inner automorphisms that we started with. Okay, so now we can give the counterexample to Maxwell symmetry of Richie solitons. So let's start with the unique two-dimensional non-abelian solvable Lie group. S1 is just the upper triangular matrices with positive diagonal of determinant 1. And let S be the three-dimensional solvable Lie group given as a direct product of S1 with the reals. And I'm going to look at two competing left invariant metrics on S, both of which are going to maximize the size of the isometry group, but neither isometry group will be contained in the other. So the first metric, we call it S1, which sits inside SO2R, acts by Mobius transformations on hyperbolic space, and it acts simply transitively. So S1 inherits a hyperbolic metric. And so for G1, we're going to take the hyperbolic metric direct product with the Euclidean metric. And this metric is actually a solved soliton. And the isometry group, or the identity component of it, is the group of isometries of hyperbolic space, which is PSL2R or SL2R mod plus minus identity, direct product with the reals. Okay, now to get the second competing metric, let's back up for a second. Let's let SL tilde 2R be the universal cover of SL2R. Every element in SL2R can be written as an orthogonal matrix times something in S1. Everything in SL2R tilde is in K times S1, where K is the universal cover of SO2R. So choose a left invariant Riemannian metric G on SL2R tilde that is also right K invariant. We can do this because the quotient of K by the center of SL2R is compact, so we can average the metric by inner automorphisms and get such a metric. So this is a construction we looked at a couple of minutes ago. And so the isometry group of this metric is left translations by the original group together with the right translations by K, again, quotienting by the diagonally embedded subgroup D, where D is the center of SL2R tilde, intersect K, which is just a copy of the integers. Okay, and this turns out to be the full isometry group, at least the identity component of it. Now, SL2R tilde, of course, acts simply transitively on itself. So you have the left translations by K and the left translations by S1. But now we have a little more freedom. We could just take the left translations by S1 and the right translations by K, and we'll still get a simply transitive group of isometries. So S1 cross K acts simply transitively and therefore inherits a left invariant metric isometric to the original metric. But K is the universal cover of SO2R. Now, SO2R is just a circle, so K is just isomorphic to R. And so S1 cross K is isomorphic to S1 cross R, which recall is our solvable Lie group S that we've been looking at. And so S is acting simply transitively, and therefore we get this metric that I'll call G2 on S, isometric to the metric on SL2R tilde. And so the isometry group of this metric is this somewhat uglier object here. Okay, so we now have our two competing metrics. Let's compare their isometry groups. So the isometry group, or the identity component for the first metric was PSL2R cross R. For the second, and its isometry algebra, the Lie algebra of the isometry group, is just a trace zero matrices direct sum R. For the second metric, the Lie algebra is the universal cover of SL2R cross the universal cover of SO2R mod something discrete. Its Lie algebra is again SL2R plus SO2R, but again, this is isomorphic to R, so SO2R plus R. So we have the same isometry algebra, but the isometry groups are quite different. You take the universal cover, you take the simply connected Lie group with the given Lie algebra, and you're quoting out different discrete subgroups of the center to get the two different isometry groups. And the reason that they really had to end up differently was because the way the isotropy algebras sit inside the Lie algebra of the isometry group. In the first case, the isotropy algebra was very nicely contained in SL2R, didn't splash over here. Whereas in the second one, the isotropy algebra was these inner automorphisms that kind of splashed between, projected onto both factors in kind of an ugly way. So what we have is these two metrics with the same isometry algebra, different isometry groups. Neither can possibly be maximally symmetric since neither isometry group is contained in the other. But they do satisfy the property that if you take any left invariant Riemannian metric, you can show that the Lie algebra of the isometry group is contained in SO2R plus TAR, the Lie algebra of the isometry groups of these metrics. So there is some kind of maximality going on. It's just not quite as nice. And so I want to introduce some weaker notions of maximal symmetry. The first one is...
Carolyn?
Yes.
Yes, can you please come back?
Yeah.
So you are saying that neither can be maximally symmetric.
Mm-hmm.
And so it's because none of these groups is isomorphic to a subgroup of the other?
Exactly.
Okay.
Yeah, they have the same dimension, they have the same universal cover, but they're different.
And how difficult is that to prove that it cannot be isomorphic to a subgroup of the other?
Well, they have the same dimension and they're connected, and they're not isomorphic to each other. And so I think that gives it to you for free.
Okay, because it's up to conjugation, right? I mean,
yes,
okay.
yes, yeah. But this one, if you look at the semi-simple Levy factors, for example, this one, PSL2R has trivial center, whereas the semi-simple Levy factor here does not.
Yeah, perfect. Yeah. Thank you.
That's another way of seeing it. Sure. Okay, so this first notion is just a very minor weakening of maximal symmetry. It's not what this example satisfied, but I want to include it. This notion is almost the same as before. We say G naught is almost maximally symmetric if for any other left invariant metric, the identity component of the isometry group of G is contained in that of G naught, again, up to pullback by nautomorphism. So the difference here is I'm only looking at the identity component of the isometry group. Well, that's certainly not satisfied by the example we just looked at. So let's weaken it further. So this is a notion of infinitesimal maximal symmetry. And the definition I'm giving is, maybe I included a little bit too much. If you want to just think of it as saying that the metric is infinitesimally maximally symmetric if for any other metric, the Lie algebra of any other metric is isomorphic to a subalgebra of the Lie algebra of your special metric, that's almost infinitesimal maximal symmetry, although what we're introducing is a little bit stronger than that. You can show it's actually stronger. So if you have a Lie group with a left invariant metric, then H sits inside the isometry group, again, by left translations. And so the Lie algebra canonically sits inside the Lie algebra of the isometry group. So we'll say a left invariant metric G naught is infinitesimally maximally symmetric if for any other left invariant Riemannian metric, there's an injective homomorphism from the Lie algebra of the competing metric into that of G naught that restricts the identity map on H, on the canonical embedding of H. Any questions?
So, and this is different from almost?
Yes. This is different from almost, like the example we looked at just a moment ago with the three-dimensional solvable group satisfies this condition. The isometry algebra is the trace zero matrices direct sum R, and any other metric has isometry algebra contained in there, and in this nice way. But if you looked at the identity components of these isometry groups, it's not the case. These are the identity components here. And again, since it's not the case that either is contained in the other, even up to isomorphism, they're not almost maximally symmetric.
No, okay. Yeah, it's at the Lie algebra level. Yeah, infinitesimal. Yeah. Okay, thanks.
However, this is kind of the only thing that can go wrong. What's happening here is, oops. So if you have a simply connected Lie group that whose Lie algebra has no compactly embedded subalgebras, so the only compactly embedded subalgebra is the zero subalgebra, then recall that if you have any left invariant metric, if you look at the Lie algebra of the isotropy group, it'll be compactly embedded in the Lie algebra of the full isometry group, and that's sort of key here. So if you have this situation where the Lie algebra has no compactly embedded subalgebras, then any infinitesimally maximally symmetric metric will be almost maximally symmetric. That is, the identity component of the isometry group will maximize. And it's a special case of this if you have a completely solvable Lie group with trivial center, that will satisfy the hypothesis. And so in that case, infinitesimal maximal symmetry will imply almost maximal symmetry. So again, what went wrong in our example here is that, S had this center R, and when we put the isotropy groups with two different metrics, one of them, had this sort of ugly way of sitting inside where it kind of diagonally it kind of splashed between the two factors in some sense. So that's sort of the only thing that can go wrong. I think I'm going to skip the proof so we can move on. So the main result I want to talk about is that every expanding left invariant Richie Soliton metric on a simply connected solvable Lie group is in fact infinitesimally maximally symmetric. And I want to emphasize that we're not assuming that the soliton is a solved soliton. It can just be any Richie soliton expanding. And there's sort of two main steps of the proof. The first step is to prove the theorem in the special case that S is completely solvable. In this case, the soliton will be a solved soliton, and it will be unique by Jorge's theorem. And then you reduce the general case to the special case. So, yes, any questions? Okay, let me, in preparation for step one, for proving the result in the case where S is completely solvable, and then the soliton is a solved soliton, I need a little preparation. So there's the beautiful theory of left invariant Einstein metrics on solvable Lie groups and of soliton metrics on solvable Lie groups, much of which was developed in Córdoba. And feel free to jump in and correct anything I say. I'm not going to summarize the whole theory, but just mention some of the things that I'll really be using. So first of all, suppose you have an Einstein solved manifold of negative Ricci curvature. Then S is a product of a nilpotent normal subgroup and an abelian group. At Lie algebra level, S is a semi-direct product N, where A is abelian and N is the nil radical. So Maxwell normal solvable Maxwell nilpotent ideal. And there's a special derivation. So there exists some element in A such that the real part delta of add x naught is, so that's a derivation of S, which is 0 on A. So really it's interesting, it's a derivation on N. And it satisfies the properties that all its eigenvalues are positive integers. And the trace of add x is a trace of delta composed with add x for all x in A. These conditions aren't so important. What's important is that there's a special derivation. This is called, for what we'll need. So delta is called the Einstein derivation. I should say the proof actually uses all these facts, but what I'm going to show you, the main thing is that there's a special derivation. The Nikolaevsky introduced this notion of a pre-Einstein derivation, which is sort of the candidates for these special derivations. We'll just look in the setting of nilpotent Lie algebra. So let N be a nilpotent Lie algebra. Then he defines the derivation of N to be a pre-Einstein derivation if it's semi-simple with only real eigenvalues, and the trace of delta composed with A is the trace of A for every derivation A of N. So very strong condition. And he proved that every, really every Lie algebra, but in particular every nilpotent Lie algebra, admits a pre-Einstein derivation delta, unique up to automorphism. And what's really key here is if you have an Einstein solved manifold, then this Einstein derivation that we talked about will be a positive multiple of a pre-Einstein derivation delta of N. That is, delta will extend trivially to the solvable algebra S by letting it be 0 on A, and that will be the Einstein derivation. And I'll mention this when we need it, but Nikolaevsky showed that the pre-Einstein derivation lies in the center of a maximal fully reducible subalgebra of the derivation. So it commutes with everything in a maximal fully reducible subalgebra. Okay, so that's the background on Einstein. Now let's move more generally to solve-solitons, which of course are a special case of, Einstein metrics are a special case of solve-solitons on solvable Lie groups. Jorge's theorem says if you have a simply connected solvable Lie group, then S admits a solve-soliton metric G if and only if the following conditions hold. So S is a semi-direct product of the nil radical and an abelian group A. So A is abelian and it's a nil radical. All the elements of add A are semi-simple. The restriction of the solve-soliton metric to the nil radical is itself a soliton, and its Ricci operator satisfies, the Ricci operator is constant times the identity plus this delta, where delta is a pre-Einstein derivation of N. Now, what we'll be using more strongly is sort of the second half of this theorem of Jorge, which I'm saying is another result. So if a solve-soliton is not Einstein, sorry, I should have said J. Lorette, sorry, because Emilio is in the room too. If a solve-soliton is not Einstein, let delta be a pre-Einstein derivation of N, commuting with A. And then you can define, it'll extend to a derivation of the Lie algebra of S. So you can define this one-dimensional solvable extension of the Lie algebra. If you look at the corresponding simply connected Lie group, S prime, which is a semi-direct product of S with an action of R, then it emits an Einstein metric G prime, and its restriction to the root to S is the original solve-soliton. So solved-solitons extend to Einstein metrics using the pre-Einstein derivation. Okay, so the only other preparation I need for the proof is a little bit of structure theory of Lie groups, which is probably familiar to most of you, but I'll quickly review it. So if G is a connected Lie group, it always has what we call Levy decomposition, G equals G1, G2, where G2 is the radical of G, which is a Maxwell connected solvable normal subgroup, and G1 is semi-simple. And moreover, every semi-simple group, in particular G1, has an Iwasawa decomposition into K1 times something solvable S1, and the S1 decomposes as an abelian semi-direct product nilpotent. So A1 is abelian. And the center of G1 is contained in K1. And while K1 might not be compact, we mod out by D, it is compact. So for example, in what we looked at a little while ago, if G is the direct product of SL2R tilde with R, then R is the solvable radical. The semi-simple Levy factor is SL2R tilde. The Iwasawa decomposition, G1 equals K1 S1 has solvable part, the original S1. The A in here, A1 is the diagonal matrices, N1 is the unipotent matrices in here. K1 is the universal cover of SO2R sitting inside here. The center of D is contained in K1. When you quotient out, you get PSL2R, and then the projection of K1 becomes compact. Okay. So again, so in the completely solvable case, let me first prove the theorem in that case. So we want to show that every solved soliton metric, G naught, on a completely solvable Lie group is infinitesimally Maxwell symmetric. And then on a completely solvable Lie group, every soliton is a solved soliton. So that will give the result in the completely solvable case. And so let me just sketch the proof for you. So the goal is to show that if you have any left invariant metric on S, then basically you want to show the isometry algebra of G is contained in that of G naught. And so let capital G be the isometry algebra of our arbitrary metric G. Write it as L times S, where L is the isotropy group and S is your solvable Lie group acting simply transitively. And German G will be the Lie algebra of the isometry group. So what we need to show is that G is contained in the Lie algebra of the isometry group of G naught. So here's an outline of the proof. First is background.
Carolyn,
Yeah.
Can you come back, please? So the difference with the almost maybe is that you are not asking here that inclusion or isomorphism is a conjugation by an automorphism, right? I'm not asking that.
Yeah. And I'm only asking for it at the Lie algebra level. And so the Lie group, the isometry groups will have the same universal cover, but they might be quotients of the universal cover by different discrete central groups.
Okay.
Although if S doesn't have a center, then we will be getting this almost maximal symmetry for free once we do this.
I see.
Okay.
I see. Okay. Thanks.
Mm-hmm. So in the background, what's behind the proof is Jorge's theorem saying that we can extend S, since S emits a solved soliton, there's an extension that emits an Einstein metric. And so the idea of the proof is to construct a new Lie group G bar. The bar here is just because it's new. It doesn't mean closure or anything like that. The form compact times S with trivial intersection. The same Lie algebra as the isometry group of the competing metric that we're looking at. In the example we looked at a little while ago, if we start with the ugly metric G2, that has sort of the funny isometry group, G bar would end up being this group here. And then using this new Lie group, we want to show that this extension of S to S prime actually gives rise to an extension of G bar as well. So you can kind of make things commute with L bar in a sense, so that you get this one-dimensional extension of our new Lie group to give you compact times S prime with trivial intersection. So this new Lie group acts simply transitively on G bar prime mod L prime. And again, G bar prime has Lie algebra equal to the isometry algebra of the competing metric. So now this S prime emits an Einstein metric. We know that Einstein solved manifolds are maximally symmetric. So that says that there is an Einstein metric on S prime that's preserved by this group G bar prime. Now, if you take that metric and restrict it to S, then again, Jorge tells us that's solve-soliton, and solve-solitons are unique up to automorphism. So basically, this Einstein metric restricts to our original solve-soliton on S. And then the fact that G bar prime preserves the Einstein metric says that implies, because of the way it's constructed, that G bar preserves the soliton metric. And so we conclude that since G bar preserves G naught, the Lie algebra G is contained in the full isometry algebra of G naught. It might not be the full algebra, but it's contained in it. And again, this was the isometry algebra, the competing metric, and so we're done. And so the key steps are these first two, the second one being the more interesting one. So to get the nicer G bar with the same Lie algebra, start with a nicely chosen Levy decomposition, take the universal cover G1, then you get a new Lie group G1 tilde semi-direct product G2 with the same Lie algebra, mod out by the full center of G1 tilde, which is discrete, and then this will give you your new Lie group. This is exactly what we did in the three-dimensional case. In that case, this would be PSL2R. This one, which I'll call G1 bar, has K1 compact. So we have this new Lie group, same Lie algebra, and the Iwasawa decomposition. K1 is compact. I'm only using bars where things have kind of changed a little bit. Otherwise, I'm using the same notation as before. And don't worry too much about this. This lemma is just saying that everything decomposes in a really, really nice way. So G bar is a compact group times our solvable group with trivial intersection. So SX simply transitively on G bar mod L bar. And now everything decomposes nicely. L bar is K1 bar sitting inside G1 bar times something in G2. So it splits between the two. Same with N. N is N1, which is in the semi-simple factor times the nil radical sitting in G2. A splits nicely. And if you put everything except N2 together, so all these things we've looked at, you get something U, which is completely reducible and acts as fully reducible transformations on N2. So now we need to get our extension of G bar to an Einstein, or to a, we extend, again, S to S prime. We want to show that extension extends to an extension of G bar. Any questions before I go on? Okay, so the key here is we have our new Lie group N2, which is part of the nil radical of S, is sitting very nicely in there. S, the Lie algebra or solvable algebra, is A plus N, abelian plus nilpotent, and each part breaks up into the two pieces. And the key step is, to extend S, you need the pre-Einstein derivation. And the key step is showing that there's a really nice pre-Einstein derivation. So there's a inner derivation. There's some x in A1, and a derivation delta 2 of N2, commuting with delta 2 commutes with everything else in G, and sort of extends trivially to a derivation of the whole Lie algebra. If you look at the sum of delta 2, the pre-Einstein derivation of N2, with this inner derivation coming from A1, you get a pre-Einstein derivation of N. And once you have that, you're good to go, because since delta 2 extends to a derivation of all of G, we can form the semi-direct product of G with this derivation, using this derivation. At the same time, S prime we can look at is the same as S semi-direct product delta 2. Normally we would take delta, but this part, add X, is already sitting in S, so we don't have to worry about that. And so this will give us our S prime and our extension of G bar to G bar prime, which is exactly what we want, because now we know that G bar prime, as we said, will preserve an Einstein metric on S prime, and therefore restricting to S, the original group will preserve the soliton. And that completes the proof in the solved soliton case. I don't know if that was too fast. Are there questions on that? And I can either stop here, or I can say a few words about the reduction to the of the general case to this case, but I think I'm probably out of time, so maybe I should stop.
Okay, so if you want to stop, we can, or you can say a few words if you want.
I don't want to hold people. Well,
okay.
It's up to you, actually. I mean, I don't know if people want to go. I probably need maybe 5 minutes to do it.
Yeah, you have.
Oh, okay. So what we have outlined the proof of is that if you have a solved soliton on an exponential solvable group, it's maximally symmetric. To get to the general case of an arbitrary soliton on an arbitrary solvable Lie group, we want to reduce to the special case. And the way we do that is actually a much more general theorem that applies to kind of all metrics. So we define an equivalence relation on the set of all solvable Lie groups of a given dimension. So let's let script R be all simply connected solvable Lie groups of dimension n. We're really looking at isomorphism classes of them. And given two n-dimensional solvable groups, we'll say that R1 is equivalent to R2 if and only if there's some left invariant metric G1 on R1 and some metric G2 on R2 on G2 on R2. I'm sorry, there should be subscripts R1 here and R2 here that are isometric. It doesn't say every left invariant metric on one is appears on the other, but there's some metric that does. It's not obvious that this is an equivalence relation. Transitivity is not obvious since the metrics may be different between different ones, but it actually is an equivalence relation. And each equivalence class contains a unique, completely solvable Lie group. And actually all this comes back around by sort of the theory of modification of solvable groups. In particular, if you look at the completely solvable Lie group, every equivalent element, every equivalent solvable group lies inside the semi-direct product of S with a Maxwell compact subgroup of odd S. And so these are sort of candidates to act isometrically on metrics on S. But the key is that you have this equivalence relation with a unique simply connected solvable group in each one. And one can prove that if R is equivalent to R prime, then they emit the same maximally symmetric metrics. In other words, every infinitesimal maximally symmetric metric on one group is isometric to a metric on the other, which is also infinitesimally maximally symmetric. In other words, any infinitesimally maximally symmetric on one of these solvable groups will actually show up as a left invariant metric on all the other solvable groups up to isometry, and they will all be infinitesimally maximally symmetric in their respective groups. And a corollary is that to determine the maximally symmetric Riemannian metrics on a solvable Lie group, it's enough to look at the completely solvable Lie group in the equivalence class. And a corollary of that is a simply connected solvable Lie group can emit at most one expanding Richie Soliton up to isometry and scaling. And the soliton, if it exists, will be infinitesimally maximally symmetric. And the reason for this is if you have any Richie Soliton, then Mike Jablonski's theorem gives us a solved soliton with that's completely solvable. Jorge tells us it's unique. And moreover, S is the only completely solvable Lie group that has any metrics, isometrics to any metrics on R. And so any other Richie soliton is going to be isometric to a solved soliton on the same S. So in other words, to G prime. And so that gives you the uniqueness and the fact that solved solitons and completely solvable Lie groups are maximally symmetric, infinitesimally maximally symmetric, says by the theorem that this soliton on R was as well. So that's the end. Okay.
Thank you, Carolyn, for the nice talk. So is there any question for Carolyn?
Let's see.
Is there any question? Well, if not, let's thank again to Carolyn.